So this presentation is for a paper submitted to this conference entitled Design of Emergency Response Manufacturing Networks, a Decision-Making Framework. The purpose of the paper is to develop a decision-making framework for the design of free-distributed manufacturing networks for the production in times of crisis. Now, redistributed manufacturing is the shift from traditional centralized production with its long linear supply chains to smaller, interconnected, geographically dispersed manufacturing facilities that are enabled by the latest advancement in information and communication technologies and are empowered by advanced manufacturing technologies such as additive manufacturing, which is commonly known as 3D printing. In other words, redistributed manufacturing is the localization of production where resources and operations are aggregated and conducted locally. Now, naturally, manufacturing systems and their accompanying supply chains are prone to disruptions of varying levels, both expected and unforeseen. Now, before the design of manufacturing systems, usually designers incorporate certain measures so that the manufacturing system can adapt to small fluctuations. But in times of emergencies or crises, such unforeseen emergencies might render manufacturing systems unable to deal with the new circumstances. For example, in times of unforeseen disruptions, which could entail unexpected spike in demand for certain products, manufacturing systems might become unable to supply the required demand quantities within the required time frame. In addition, even if a manufacturing system was able to produce the required quantities, the supporting supply chain might be disrupted and hinder the transportation of products within the required time frame. For example, if the required quantities have been produced in the place of origin, there might be no way to transport them to their destination within the required time. This becomes apparent during natural and man-made disasters such as earthquakes, hurricanes, and wars, for example, where transportation from one location to another might become impossible, and therefore product transportation is affected. Therefore, in this paper, a framework for the design of redistributed manufacturing networks that enables the localization of production in affected areas so that these areas are not isolated is developed. The framework consists of interacting optimization and simulation models that operate in an iterative manner. The optimization model, which is an integer linear program, provides decision for the location of production facilities, allocation of production to demand points, production schedules, and delivery amounts at each planning period. After the optimization model identifies the optimal values for decision variables, which then results in the manufacturing network being generated, the decisions variables values are stored in a shared database. This database then is accessed by the simulation model, which is an agent-based model. The simulation model then uses the optimization model's outputs as input parameters and evaluates the generated network under uncertainty in a stochastic environment. The simulation model then runs several replications each with different values for the parameters, so that an insightful output can be produced from the simulation model as it is stochastic. And then the mean of the simulation model's output is taken to provide insight into the performance of the production network. Then the simulation model, after performing several replications, sends the feedback to the optimization model through the shared database for for the chosen performance criteria, which in this instance is the frequency of the occurrence of unmet demands or inventory shortages. These feedbacks are then transformed into constraints that the optimization model takes to guide its search for the optimal values. The optimization model then runs again and generates a new production network based on the simulation model's feedback. Then the simulation model again re-evaluates the performance of the system under several replications so that a meaningful output is produced. This process continues iteratively until the predefined performance criterion is met or a steady state is achieved. A steady state is when the improvement in the performance of the production system ceases to occur in subsequent optimization simulation iterations. This will be clear later on in this presentation. Now, to validate and test the framework, it has been applied to a case study inspired by the ongoing outbreak of the coronavirus pandemic, which caused severe shortages in personal protective equipment experienced in some areas during the early stages of the outbreak. In Italy, for example, the shortages of face shields and face masks dangerously affected frontline healthcare providers. So in this research, the local production of face shields is assumed. The region of southeast England, which is the country's most populous region, has been chosen. The locations of existing hospitals are assumed to be the demand points for the face shields. Now, the production for the face shields is assumed to be done using additive manufacturing, which is commonly known as 3D printing, and has been demonstrated earlier during the pandemic to be able to produce face shields efficiently. Face shields in particular are chosen because they are not subject to strict regulations such as other medical equipment. Now, all hospitals in the southeast region of England are assumed to be potential locations for redistributed manufacturing plants where additive manufacturing equipment are placed to produce the face shields. The figure here illustrates the chosen area along with the locations of hospitals, which are also the locations of potential production plants. Now, this slide here shows the input parameter values used for the framework's models, along with the probability distribution shape parameters. When applied with minimizing the total supply weighted distances traveled, the framework generated the production network depicted here in this slide. 5 available AM equipment were chosen, and the framework placed them as depicted in the figure here. It took 9 optimization simulation iterations to reach a steady state where the framework ceased to improve the system's performance. In the first optimization simulation iteration, the average frequency of the occurrence of unmet demand was around 18 occurrences. This figure then considerably decreased in the second iteration, where it became around 8. Then gradual improvements continued to take place until the 9th iteration, where there was about an average of 4 occurrences of unmet demands or inventory shortages in the entire production system. Beyond the 9th iteration, the framework did not result in improved performance in this regard. The figure on the right here depicts the difference in performance of the production network between the first and the last optimization simulation iterations, where the hospitals that initially experienced the largest numbers of unmet demands all in the last iteration averaged less than 0.5 occurrences of inventory shortages. To compare the system's performance with that of a traditional centralized one, a centralized production system has been established, modeled, and applied to the framework. It can be seen from the figures up that the average distances traveled is considerably less in the redistributed manufacturing scenario, which is naturally caused by the decentralization effect where less distances are traveled between production plants and demand points. As for the utilization of production equipment, which in this instance are 3D printers, the difference in machines utilization is negligible. However, the utilization of machines per locations considerably changed. This is because at each iteration of the framework changes the production schedules and the allocation of demand from each production site. In conclusion, redistributed manufacturing provides a means for production in the event of disrupted supply chain. Lead time significantly improves due to shorter distances traveled, and service levels measured by the frequency of the face shield shortages significantly improves when applying the framework to design a production network. And finally, redistributed manufacturing could also be used as a strategic tool for the strategic long-term production rather than a temporary solution